to it. It says find the measures of angle P, Q, and angle R. Notice that you have an equilateral triangle, and like I just said, not only is it equilateral, but it's also equiangular. So, Erica, if all three sides are the same, all three angles will also be the same. How big are each of them, Erica? They have to add up to 180, right? So if all three are the same, each of them must be 60 degrees, 60 degrees, and 60 degrees. Equilateral also means equiangular. Next problem, and this is kind of going back to what we did previous. It's kind of skipping all around. It says complete each statement, explain why it's true. We're back on, we're back talking about now isosceles triangles, not necessarily equilateral and equiangular. It says BT. We're wanting to know BT is also congruent to what other side length. Carson, what's BT going to be congruent to? Just two letters. VX. Okay, the other side. And honestly, we just look at that, right? And kind of know that's true. But let's talk about why that's true. First off, how many triangles are there? I like this question. How many? There's three. There's a small triangle here. There's a small or medium-sized triangle, and then you have the large triangle. In the large triangle, which the large triangle is VTX, in the large triangle, you have two angles that are the same. Notice that this angle is equal to this angle, and both of those angles are in the large triangle. That makes the large triangle isosceles. If two angles are the same, that means two sides are the same. If these are your base angles, then these are your legs. Okay, moving on. What if we know that UT, well, we're given that, right? UT is congruent to YX is congruent to what other side? Same thing. Look at your small triangle. In the small triangle, you have two angles that are the same, therefore you have two sides that are the same. So not only does UT equal UW, but it also says that UW is equal to YX, so that's in the middle here. We're going to put our UW. All three of them are equal. And there you kind of see a picture of the transitive property. You see that? UT is equal to UW. UW is equal to YX. That means that UT is also equal to YX. Transitive property right there. What about VU? And then we'll move on. You would think VY, right? Here's the big question. There's two ways to explain it, by the way. Anybody have any idea why they think that that's true? You can use that fact from the last problem. We know that UW and UT are the same. That makes sense to everybody because it's isosceles. If these are the same, those are the same. We also know that from the first problem, VT is the same thing as VX, correct? Well, VT is the same thing as VX. We also know that UT is the same thing as YX. Then obviously, you see the subtraction property. You've got that whole VT is equal to the whole VX. Well, if you took off these pieces, off of each of those bigger pieces, which are also equal, that subtraction property, then you're going to be left with VU and VY being the same. That's what we say. Y'all probably like, well, you can just tell a whole lot better than that. Here's the second way of doing it. My question for you, from what is given, Carson, can we say from just by looking at that picture, can you say that VUY is an isosceles triangle? Just by what they're giving you there. No. No. VUY, as it is given, if we took all this off right here, guys, VUY is not necessarily an isosceles triangle. You don't know that. And now if we knew as isosceles, we could say that the legs were the same, but we don't know that they are. So that's the reason I'm having to go through these other steps. I don't know if that's isosceles or not. Question. Is this line parallel to that line? Yes. Sydney? How do you know that those lines are parallel? There's your hint. Use that as a transversal. Sydney, what kind of angles are these? Good. That's right. Those two angles are corresponding angles. Since corresponding angles are the same, we know those two lines are parallel. Since those lines are parallel, we know that also, what if this is a transversal? We know that these corresponding angles would also be the same. So now, is that an isosceles triangle? Yes. And are those sides the same? Can't just say, well, it looks like they are. That's enough of that. Moving on. Trick question. What kind of triangle is that? What's that like? Anybody know what kind of triangle it is? Well, you're given that this side is equal to this side, right? So that has to be isosceles. That has nothing to do with, well, it looks isosceles. It has nothing to do with that. What kind of triangle does it? Anybody see something else that jumps out at them? And by the way, you might want to start this so you notice this will be a test question. It's on there. Is it more than an isosceles triangle? Yes. If these two angles are the same, wait a minute. Is that the base angles? I thought these two were the base angles. If these two angles are the same, then what other side is going to equal AC? If these two are the same. Then AC would equal BC. Because if that's your base angles, well, spin that thing around. Set it on its base, then that would mean that AC and BC are the same. Well, AC is also equal to AB. So by the transitive property, AB is also equal to BC. They're all equal. That's an equilateral triangle. Again, for the reason of, we were given that these two sides are equal. Since we know these two base angles are equal, we also know that these two sides are equal. So my question now is, how big is angle C? Because you have to know that before you can work this problem. That's the reason I like this problem, and the reason I put it on the test. How big is angle C? Also what? Well, also, it will be 60. You're exactly right. This angle's going to be 60. This angle's going, and that's going to be the easy way. Since it's equilateral, it's equal angular, and we know that every angle is 60. So why not just say, you know what? 2x is 60. 2x is 60. 2x is 60. X is X is 30. Done. And Hunter set me up an equation here. This side is 4y minus 5. What will 4y minus 5 equal? Be careful, that's a side length. It's not an angle. This side is equal to 3. There we go. All the sides are equal. If it's equilateral, it's equal angular. If it's equal angular, it's equilateral. All the angles are the same. All the sides are the same. We solve this by adding 5 divided by 4. We get y is 2. Next problem, find the value of each variable. I'll give you a second to look at it. Y will be pretty easy. But trying to figure out what x is, that might require a little bit of thought. Destiny, help me with y. Since it's a little bit easier, help me with y. Set me up an equation I can use to solve for y destiny. 4y minus 2. Good job. It's an isosceles triangle. The lengths are the same. Okay, they're equal to each other. We set it up 4y minus 2 equals 2y plus 2. We move these two y's over here by subtracting. I'm left with 2. We move this minus 2 over here by adding. 2 plus 2 is 4. So y must be 2. Always be careful. Okay, find the value of each variable. I'm good. Y equals 2 is your answer. You can always check it by going up here and plugging it in. If y is 2, you have 8 minus 2, which is 6. You have 4 plus 2, which is also 6. Now let's try to find out what the angles are equal. Vanessa, any ideas? How would you work this? Six x plus 8 equals what? Does it equal 80? Question mark. Let's talk. In an isosceles triangle, two of the angles are equal, correct? But the question is it these two angles? There are two types of angles in an isosceles triangle. There are base angles. There are base angles. There's two of those. And there is a vertex angle. And the rule is, in an isosceles triangle, the base angles are always congruent. But where are the base angles located? Okay. If you've got a setting on its base, you'll have the two legs on the left and right side. So the question is or are those two angles your base angles? No. What's this one called? That's the vertex angle. So actually, these two are not equal, but these two are equal. So there's you can't really set it up like that. Can anybody tell me what 6x plus 8 will equal? Second. All three will equal 180. We could do it like that. One way of solving it, let's do it his way first. One way of solving this would be 6x plus 8 plus 80 plus, well, we don't know what this is, right? Isn't it also 6x plus 8? You could solve it like that. They all equal 180. That's one way of doing it. What if I want to make it a little bit easier? Anybody tell me what just that angle is going to equal? Let's say it from the back. 50. Where in the world did they get that? Watch very closely. If this is 80, all three add up to 180. So that means that these two are going to add up to 100. Well, aren't they the same? So if they add up to 100, would that not be 50 and 50? So therefore, 6x plus 8 equals 50. Might be a little bit easier. Subtract 8, divide by 6. Anybody get x? Perfect. So x is 7, and we got y is 2. I've already taught you this theorem without you even knowing it. Let me remind you of something I told you about isosceles triangles. If you have an isosceles triangle, it is symmetrical. If I drew a line of symmetry, split it right down the middle, we can see that left side, right side, you can flip it across that axis of symmetry. And you also knew that these angles would be equal. Well, we can go a step further. Look what it says. The bisector of the vertex angle. Everybody remembers what the vertex angle is? The bisector. If I cut that vertex angle in half, it says the bisector of the vertex angle of an isosceles triangle is perpendicular bisector of the base. If I drew a line that bisects, that cuts this angle in half, was that not that axis of symmetry, that line of symmetry I was talking about? Not only will it cut this in half, but it'll be perpendicular to the base. Well, think about it. I told you it cuts the whole triangle perfectly in half. Well, this line right here, this angle is equal to 180. Would that not mean it would have to be 90 and 90 if it cut it perfectly in half? Would it not also mean that this line segment would have to equal that line segment? Okay. So that right there, I want you to picture that. Anytime you draw a line that is symmetrical, that cuts it into two pieces of symmetry here, the left side and the right side are the same. You're going to have an angle bisector. You're going to have a perpendicular line, perpendicular bisector. These segments will also be the same. These angles will all be the same. The triangle on the right side is a mirror image of the triangle on the left side. Y'all see that? So that's your new theorem. And if you just want to draw this and just make sure that you know anytime you have an isosceles triangle, that's going to be the case. If you draw a perpendicular bisector, it's also going to be the vertex angle bisector. If you draw a vertex angle bisector, it's also the perpendicular bisector. First problem. If the measure of angle L is 58 degrees, the measure of angle LKJ, how big is it? Okay. Again, what they've done here is they've cut this triangle perfectly in half. Guys, that's going to be a right angle. because they're both right angles. So what it's asking is, if this is 58, how big is this? 58, 90, and 32. All three angles have to add up to 180, or the shortcut of that, remember the corollary, stating if you've got a right triangle, the two small angles have to add up to 90. So if you have a 58, you can just subtract that from 90, and that'll give you the 32. But again, anytime you draw an angle bisector, it'll also be a perpendicular bisector. Next problem. If JL is 5, how big is ML? See how easy it is. What do y'all think? 2.5. Each of those would be 2.5. Again, this would be perpendicular. This angle is the same as that angle. This angle is the same as that angle. We're good. Okay, everything's the same. This side is the same as itself. Okay. If JKM is 48, JKM, if this is 48, then angle J. What do y'all think about that one? If you have a 48-degree angle, again, this line, not only does it cut this angle in half, but it also cuts this angle in half, 90 and 90. 48, 42, 90. This would also be 42. This would also be 48. If this is 6, this would be 6. If this were 3, this would be 3, and so on and so forth. One more, and I think we're getting the point. If angle J is 55 degrees, you don't have to add, it doesn't ask for it, but angle L is also 55 degrees. Since it cuts this in half, it also cuts this angle in half. That's 90. How big is JKM? Anybody, how big is it? $30. Good. And that would also be 35 degrees. This side's equal to this side. This line segment's equal to this line segment, and so on and so forth. We're getting the point now. Okay. Similar, but not really the same thing. Now we're back talking to primarily just about isosceles now. You don't have a line of symmetry. You don't have one cutting it in half. You have two different, you have two different isosceles triangles here, and you're looking for the value of x, and you're looking for the value of y. Question. Brianna? Since this is an isosceles triangle, does that mean these two angles right here will be the same? No. These two angles are not base angles. If these are your two equal legs, these are your two equal angles. That makes sense. You wouldn't say these are equal legs, these are equal angles. If these are the equal legs, these are the equal angles. Same thing over here. If these two are the equal legs, these base angles would be the equal angles. So with that said, if this is 50 degrees, then this one up here would be 50 degrees. Kirsty, again, the three angles of a triangle have to add up to what? Perfect. So if this is 50 and this is 50, that adds up to 100. Anybody tell me what's left? 80. Perfect. Good job. Over here, these two angles are the same. This one's 100. That leaves me with 80. So y would be how much? 40 degrees, half of that. And this one would also be 40 degrees. That's nearly a square, isn't it? 40 and 50, that's a right angle. That's a right angle. That's 80 and 100. That's actually what's known as a kite. Okay? We'll talk about kites later on in chapter, I believe, 6. There's a good problem. Pretty sure this one's on the test. Cole. 110. Let's find all the angles. If this is 110, Cole, these two form a linear pair, so how big is this one going to be? Perfect. And if that's 70, Jackie, what other angle would also be 70? Perfect. Because again, here's your two equal sides, here's your two equal angles. This is also 70. Stephen, 70 and 70 is 140. Perfect. The three have to add up to 180, so that would leave 40 for that. We don't have to know it, but that's also 110. There's another way you could have worked that. That theorem that we always forget about. Why do I know we forget about it? Because honestly, I forget about it too. Could you use the exterior angle theorem? Isn't that an exterior angle? And once I knew this was 70 and this was 70, I could have also said, okay, These two angles have to add up to 110, so we could have done it that way as well. Another one. Goodness. This one is the new stuff. You have an isosceles triangle. You have a line segment that's going to cut that isosceles triangle in half. The reason I know it cuts it in half is because it cut that in half. Those angles are the same. Therefore, you have a line of symmetry. If this is 52, then this is 52. If this is 4, then this is 4. Well, how are we going to find that? We can do it like this. This is a 90-degree angle. 52, 38, and 90 adds up to 180 because you have 3 triangles now, and that would also be a 38-degree angle. Any questions? Okay. When you have 3 or more lines crossing at a single point, that point is a point of concurrency. And the lines are called concurrent lines. Once again, anytime 3 or more, it could be 3, 4, 5, 6, but it has to be at least 3. It can't be 2. Okay? This is not a point of concurrency. That we don't refer to that. It says when 3 or more lines intersect at a common point, we call that a point of concurrency. There are 4 special types of points of concurrency. We're going to address 3 of them, and today we're probably, like I said, we're probably just going to hit one of them today. But again, P is a point of concurrency. Your first special point of concurrency is called a circumcenter. In a triangle, okay, something we need to review, a perpendicular bisector. Talked about it for a good while now. If you have a line segment, a perpendicular bisector has 2 special features. Number 1, it's perpendicular to the line segment, and number 2, it bisects the line segment. So it would cut it in half, and it would also be perpendicular to it. That's a perpendicular bisector. If you have a triangle, and you draw the perpendicular bisectors of all 3 sides, all 3 of those perpendicular bisectors will cross at the exact same spot. That's weird. And I'll prove it to you in just a second, maybe. And the spot where the perpendicular bisectors cross is called a circumcenter. And you can write it like this for those of you that have not started. A circumcenter is the point of concurrency. Point of concurrency of the perpendicular bisectors. So let's review this. I need to review the perpendicular bisector theorem. Let me kind of draw pretty close. Perpendicular bisector. If a point, see if you can tell me. If a point lies on the perpendicular bisector, let me just put a point somewhere on here. About right here. What's special about that point? If a point lies on a perpendicular bisector, what's true about it? Think of it like this. Again, here's the room. And what I'm going to do is I'm going to go to the middle of the room and I'm going to back up and I'm going to stand right here. Okay. Again, I'm standing on the perpendicular bisector of the room. I'm at the middle and I walk straight back. Okay, perpendicular bisector. What was true about where I was standing? Equidistant from where? The corners of the room. So it's the same thing here. If a point lies on a perpendicular bisector, it is the same distance from this endpoint as it is from this endpoint. Y'all remember that? So let's think about this now. Let me take and blow up this drawing here and show you what's special about a circumcenter. We're kind of combining a lot of the stuff that we're learning. Okay, what we have here, we have a perpendicular bisector, and this point of concurrency. Question. Since it lies on the perpendicular bisector of this, okay, here's your line segment. We took and we drew a line perpendicular to it and we bisected it. So this is a perpendicular bisector. So since this point lies on a perpendicular bisector, is it not the same distance from this endpoint as it is from this endpoint? I'm going to put 3 tick, actually I'm going to put 4 tick marks. Okay, now let's look at this side. This line segment. This is a perpendicular bisector. Since this point also lies on this perpendicular bisector, would it not be the same distance from this corner as it is from this corner? Same thing here. This point lies on this perpendicular bisector, so it's the same distance from here as it is from here. So what's special about a circumcenter? The circumcenter is the point in a triangle that is the same distance from all 3 corners of that triangle. So what can we do with a circumcenter? I challenge you sometime. Circumcenter.
May I have your attention, please?
I challenge you to do this. Sometime draw yourself a triangle and try to draw a circle around that triangle. And as you're drawing that circle, when I say draw a circle around a triangle, as you draw that circle, I want you to hit all 3 corners of that triangle. It's hard. That's not very easy. That's what a circumcenter does. Think about it. Since a circumcenter is the same distance from this corner as it is from this corner as it is from this corner, you know what we call that distance? A radius. And we could take, and everybody knows what a compass is, right? Not a north, south, east, west compass, a draw circle compass. We could take our compass and we could open it to that radius length, and we can now, with this as the center of our circle, with this as our radius, we can now draw a circle that should hit all 3 of those corners of that circle, or excuse me, of that triangle. Let's see if we have a problem. Yeah, let's try this one, then I'm done. Plot the following 3 points and then find the circumcenter. You got the point negative 5, 6. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6. This is what the problem will look like on your test. Might not be the same one. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6. And negative 5, negative 1, 2, 3, 4. I once again remind you, that was terrible. Let's try that again. Not gonna let me do it. I'm gonna try to draw it freehand again. Better. A circumcenter is the point of concurrency of 3 perpendicular bisectors. So what I need to do is I need to draw the 3 perpendicular bisectors to see where they cross. A perpendicular bisector is perpendicular to a line segment and it cuts it in half. Help me with this. Since it cuts it in half, since I'm going to cut this since I'm going to cut this line segment in half, what point will the perpendicular bisector pass through? Thank you. It's called a midpoint. So again, now do you see how everything's starting to fit together? Do we learn about midpoints? Yeah. Do we learn how to find midpoints? Yes. Do we have to use our midpoint formula on this? No. Just count. Okay. From negative 5, 6 over to 7, 6, I think that's a distance of 12. So just count over 1, 2, 3, 4, 5. Just cut it in half. Count over 6. Now how in the world am I going to do a perpendicular line to that? It's a horizontal line, I guess. Draw vertical. Okay. That line will be perpendicular, correct, to my first line? That's the perpendicular bisector. Same thing on the right or left side. This one's going to be pretty easy too. The distance from negative 5, 6 down to negative 5, negative 4, that's a distance of 10. So I believe you can count 5 from either endpoint, and that's going to be the middle. Draw a horizontal line now. Okay, stop for a second. Think. I'm looking for the point where the three perpendicular bisectors cross. All three perpendicular bisectors will cross at the same point. Do I have to draw all three? Where's the third one going to cross? Listen to what I said. All three cross at the same spot, right? Is the third one going to cross right there too? Yes. Do you have to draw all three? No. If you're confident, right there is going to be your point of concurrency. If you need to, go for it. And I want to show you the next one anyway for this reason. How in the world do you find the perpendicular bisector of a slanted line? Well, this is the point -5, -4. This is the point 7, 6. Well, first off, perpendicular bisector is going to pass to the midpoint. That's the reason I've been doing all this midpoint stuff with you. Add the x's, divide by 2, you get 2 divided by 2, which is 1. Add the y's, divide by 2, you get 1. 1, 1, that line's crooked. 1, 1 is the midpoint of this line segment. How do you draw a line perpendicular to another line? What do you know about perpendicular lines? What's true about slopes of perpendicular lines? Opposite reciprocals. So what I need to do is I need to draw a perpendicular line to this. So what I do, first find your slope. 10 over 12 is my slope, or 5/6. So if I want to draw a line that's perpendicular to that, I'll simply draw a line that has a slope of -6/5. So go down from this dot is on the line, go down 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, or go up 1, 2, 3, 4, 5, 6, left 1, 2, 3, 4, 5. And it is perpendicular. Your point of concurrency is right there, actually at 1, 1. So what does that mean? If you wanted to draw a circle around this triangle, you would set the center of your circle, because the distance from here to this corner is the same as the distance from here to this corner is the same as the distance from here to this corner. You would set this as the center of your circle. You would open your compass to a radius of this length, and with that radius set, you would start drawing that circle, and it should hit all three of those.